they occasionally goes past it, but then it quickly readjusts and goes down again because they have a bumper crop of food, so they have lots of babies. Okay, so the population goes up past it. What happens? Now they get too many, and there's a normal climate and normal harvest, and consequently a lot of these die. So it goes up past it and then comes back down again.
Does it fall a lot during like November?
Well, that's built into the winters and things like that. Matter of fact, in my my course, my Mathematica 170, one credit course in January is on the books now. I don't know if you noticed that. You can sign up for it. That may be one of the projects I'm going to be doing. There's 5 days that it meets, one credit course in January, 1 week.
Math 170?
Yeah, 170, one credit. I may do one of these logistics functions.
So does it fall during?
It's 3 hours a day.
Is it really? For 5 days a week?
Yeah, well, 1 week of 5 days, not 5 days a week for 10 weeks. It's 1 week, 5 days.
Oh, okay.
You got it?
Yeah, I thought it was 5 days a week for 3 hours.
It is 5 days a week, 3 hours a day, but it's only for 1 week.
Yeah, I know.
There's a total of 15 hours.
That would be crazy.
All right, anyhow, I got to figure out what projects I'm going to do. But anyhow, I just want to mention this. This is the point of inflection. You don't have to wait until this time. This may take 20 years or so for that population to reach carrying capacity where you can predict it reasonably well. But if you have the point of inflection here, as soon as it starts bending, okay, and you can do this mathematically, find this point of inflection, you can determine the carrying capacity ahead of time, which is really useful information. As soon as they start off with exponential growth, and then it starts slowing, and as soon as it starts slowing, at that time, that point of inflection will give you the carrying capacity of the environment. Okay, the mathematics of population growth is amazing. It's really cool, and a lot of these systems end up to be chaotic systems, which means you can't even predict some of these outcomes. Minor perturbations in initial conditions lead to unknown outcomes in population. Weather is another thing that leads is chaotic systems. It's just so complicated how these variables impact each other.
It's nature.
It is nature.
That's why the.
I know, that's it. And nature's even changing, I know it.
That's why the weatherman's not.
No, they aren't. All right, anyhow. Okay, I just wanted to throw that in there.
Record last ones?
Excuse me?
The last one?
I didn't do the last one yet.
No.
Oh.
Last class.
Last class, so you recorded.
We had that.
No, we
after
didn't.
class.
We came to this conclusion after the class ended.
Hey, you were complaining
Like,
like
this might
right
be good
before
for
class.
Danny. So
That's
we're
what
gonna-
happened. That's what happened, because the whole class said, listen, we got to do something for Danny. We have to make sure, but it was too late. Yeah, that's true.
We've gone way too far.
All right. But for future Dannys, that's what the thing is. Future
Shouldn't have showed
Danny.
up today.
What's
I
that?
shouldn't have showed up today because it was.
Yeah, that's true, you know.
I guess I'm.
No. Okay, last question. F of x is equal to 4x cubed minus 9x squared minus 15x plus 5. Now, cubic polynomial, what we want to do is find point of inflection. Let's take the first and second derivatives, and we'll set the second derivative equal to 0. So first derivative.
So we didn't have to do that graph that we did before all the time? Why did we do that graph?
Which one?
The graph, the last one you said.
The logistics function?
No.
Oh.
Yeah, professional. Did they ask for a graph?
No, they did not ask for a graph. I did it just so we could see what it was beforehand. I went beyond the question. Okay.
Oh, wow.
Nice visual.
No graphs for the test, right?
No graphs in the test. No, you know what? I'm going to give you two functions. I'm going to give you a cubic polynomial, like I said, and I'm going to give you a rational expression. And then I'm going to ask for where it's increasing and decreasing horizontal tangents. And I think on one of them, I ask you to pick the correct graph. I'll have the computer generate 4 graphs, one of which will be correct. I'm pretty sure that's what I have you do.
Why, how do we find like where it's increasing and decreasing?
You have to find where the first derivative is positive and where the first derivative is negative. That's what you're going to have to
How
do.
do we do that?
We'll have to do another problem. Let's do this one
Does Damien
first.
still have those notes from last class?
You have those?
At home.
Oh, you're going to have to go to Damien's house, okay?
No, you can take a picture of them for next time.
Are you saying you don't wanna go over it?
Yeah, we do. We do want to go over it.
He was like,
No, the rules, the thing is he had the rules on those.
Yeah, I had them all there, but well, maybe we could do it on this one. Let's do it on this one, okay?
that's what I was saying. That's what I meant.
Well, the thing is, I'm looking at this and I'm thinking that I'd like to do it on this, but it looks to me that they purposely gave you one where you have to do a second derivative because the first derivative is real nasty. But that's all right, we can do it, because we can do it.
No.
It restarts after 20 minutes, I think. Or like after a half an hour.
Why?
So the files are smaller.
Why?
So we could put them on YouTube without a problem, or whatever?
I think Z puts them like
It's just a
hourly,
word.
but then I think they set up something about copyright. If they're too long or something like that.
Really? Wow.
I'm
All
not
right, well, let's do the first derivative, 12x squared minus 18x minus 15. There's our first derivative. I'll tell you what, let's try to do it, even though it may be a little bit nasty, because the problem's not set up to do first derivative, positive and negative, but let's do it. All right, here's the first derivative. Here's what we want to do. We want to graph this polynomial, and what I want to do is find out where it's increasing, where it's decreasing, where we have horizontal tangents, okay? And then I'm going to take a second derivative and find out where it's concave up, concave down, and a point of inflection, okay? This is going way beyond what the question is asking, but this is the kind of thing that you should know for the test, okay? So I'm doing it to review what we did last time. All right, first thing I would do here is factor out a 3. Then I would see if I could factor this expression. See, I want to know when the first derivative is positive, where it's negative, and where it's equal to 0. Because that will tell me where the function's increasing and the graph is rising, where the function's decreasing and the graph is falling, and where we have horizontal tangents.
So would you try finding where?
I would try to, I would try to factor this first. I'm not sure I can factor this.
Pretty nasty.
I need a plus or a minus, and I have to get a 6, I get 10, I get an 8. If we had an 8 there, we could do it. We got a 20, we got a 1. It can't be factored. I'm going to use the quadratic formula on it to get my zeros.
It's 1/4 times 3 minus the root of 29.
Oh, wow, nice, thank you.
Go from mouth up.
Is that right? Oh, my
Oh,
gosh.
I thought that was a calculator.
All right, wow. All right, give it to me again, what is it?
It's 1/4 times, in parentheses, 3 minus root 29. And the other one is
It's plus.
1/4, in parentheses, 3 plus root
Yeah,
29.
yeah. Wow, that's a, that is really amazing,
I do that
okay.
all the time, I
That is something. Okay, so here's what I'm going to do. I am going to graph the first derivative.
probably could do this.
Yeah, you probably could just say graph this thing, it'll probably do it. Okay, let me get an idea of what we have. The square root of 29 is between 5 and 6. So we get 3 plus 5, that's 8. Around 2 is 1 point where we have a 0.
Times 1.14.
Yeah, I did that. I already did it. It's between 5 and 6. That's about between 8 and 9, but 1/4 of that. So it's in here somewhere. This point right here would be, and the other one's over here somewhere.
It's like negative 0.5
Yeah.
around there.
Okay, it's like closer in, like this. Okay. And this point would be this. And you got a parabola that looks like this. This is the first derivative. Okay? Now, what does this tell me? This tells me, as far as the function is concerned, here's what I know about the function and its graph. I know that the function is increasing when x is less than 1/4 times 3 minus the square root of 29. Because when x is less than that, the first derivative is positive. It's also increasing when x is greater than 1/4 3 plus the square root of 29. Say, Trent, can you give me a decent approximations for these?
Negative 0.59, or negative 0.6, really,
Okay,
and 2.1.
good, thank you. Okay, so that's what I have. For those values, the function is increasing and the graph is rising. Okay, that's where the first derivative is positive. This function is decreasing. Okay, between those two values, where the first derivative is negative. I'm going to use the 0.6s and the 2.1s. Okay? That's where the function is decreasing. So I have a function that's increasing, decreasing, increasing.
So it's all, where it's decreasing is just less than 0.
Where the first derivative is less than 0.
Yes.
A function may be positive, but it is decreasing during that interval. It may be positive or negative. Okay? But the first derivative being negative tells me that the function is decreasing.
So just make sure we don't confuse it with actually decreasing.
Yeah, you got to keep the two straight.
Yeah.
And there's one important thing here. Where the first derivative is equal to 0 at these 2 points, that's where we got horizontal tangent lines. All right, now here's what I hope, if you could do this, Trent, that would be awesome. Find the function at these two values, negative 0.6. So that means substituting it into the original function to find the value of the function there.
Yeah.
Here, I'm going to get an approximation here. And the value of the function at 2.1.
So while he's doing that, I don't understand what was the increasing one.
All right, for the increasing one, when does the function increase? When the first derivative is positive. That's when the function increases. Here's my graph of the first derivative. Where is this positive? Well, it's positive when it's above the x-axis. That's where it's positive. That occurs when x is less than this number here, this 0, 1/4 times the quantity 3 minus the square root of 29. That's what we've got. When x is less than that number, first derivative is positive, and the function is increasing.
Because do you understand what I'm saying? Like, if you look from the left, like, it looks like it's decreasing.
No, wait, okay, hold on, you gotta be careful. This is your first derivative, okay? That's not the function,
Can you put it down a little bit? I'm sorry. Thank you.
okay?
On that graph.
This graph is the graph of your first derivative.
It looks like it's decreasing until it
Okay,
gets to 0.
we don't care where it's decreasing. We care where it's positive or negative. Where this first derivative is positive, and it's positive here and here, that's when our function is increasing. That's our function here. I have not done the graph of that yet. That's what we're looking for, that graph. But I do know that graph is rising, function's increasing, for these values of x where the first derivative is positive, and for these values of x where the first derivative is positive.
That's weird.
That shouldn't be weird. That should
If you
be,
looked at it like just generally looking at it, then it would look like it's increasing at 0 to infinity.
okay. Yeah, and that function, that graph right there is increasing for those values. What you said was a true statement. But all I care about with that function is where is it positive and where is it negative, because that tells me the behavior of the function that I'm looking for, okay? All right, do we have these two values, Trent?
Yeah,
At negative 0.6, what do we have?
9.896.
9.9, say?
Yeah,
Good enough. And this one?
negative 29.4.
Okay, good enough. Those are very important points. Those are where we have horizontal tangents. That's where the first derivative is equal to 0. Okay? Okay, so this is where the first derivative is equal to 0. at these values. And at those values, my function is 9.9 at this value and negative 29.1 at that value. Where the first derivative is equal to 0, I have horizontal tangent lines. Okay? So here's what I have right now. You ready for this? We have the following. At negative 0.6, the function's 9.9. Okay. At 2.1, the function's negative 29, or it's way down here somewhere.
2.1 and negative 29.
Yes. Okay.
That's just our horizontal.
Okay. Those are horizontal tangent lines. We got a horizontal tangent here, and we've got a horizontal tangent here. I also have an y-intercept at 0.5. Okay. I know that this function is increasing when x is less than this negative 0.6. I have a function that's increasing. The graph is rising. That's what my first derivative is positive. It's falling and then rising again. Here's what the graph looks like. It's going to be rising, horizontal tangent, falling, horizontal tangent, rising again. This is my function right here. Okay? We're going to verify this now with the second derivative. This is the actual question that they're posing. What is the point of inflection? Well, just by looking at my graph, as crude as it is, can someone give me an estimate as to where the point of inflection is here?
Like 3, like...
3 is over here somewhere. I don't want 3.
Oh, because you have 0.5 over there.
I have 0.5 here, yeah. But what's the x coordinate? 2.1 is here.
Probably like 1.
Not drum-
Yeah, 1 is good. It's right in here somewhere, around 1. Okay, is everybody with me on this?
Yeah.
You with me, Danny? Okay, here we go.
Like between 2, negative 0.6, correct?
The point of inflection is definitely between those two values, yeah. And it looks like it's down below here more. It looks like it's about 1, but my graph is off, so I don't know. We'll see. Here we go. Let's take the second derivative and set it equal to 0, but let's take the second derivative. You get 24x minus 18, and let's set it equal to 0. It's my second derivative. Okay, add the 18 divided by 24, and divide by 6s. 3/4 is good. 3/4. The value of the function at 3/4, I don't know, can you do that one, Trent? Thank you.
Negative 9.625.
So you put the,
Go ahead.
so, did you put the 3/4 into the?
Original function.
Oh, the original function.
Yes, yeah. That's that F here.
So that's the point of inflection.
That's the answer to this question.
Second derivative equals 0.
Yeah, that is correct. Okay? And one further thing here. When x is less than 3/4, the second derivative will be negative, and it's concave down. When x is greater than 3/4, this will be positive and concave up. This is the point of transition. This is the inflection point. That's what you had to do. That was the answer to your question. But we went way beyond, okay? Way beyond. Does it make sense? You're gonna have to try some of these problems, okay? Try some of the homework, and then ask questions on Thursday, okay?
Or I'll just email.
Email, you can always email me, that's fine.
What is this?
What's that?
I'll just annoy you with emails.
You can use the graphs too, they really help to verify the
Yeah,
answer.
emails don't annoy me.
Well, sometimes when you say you want to try another version, they have the same version, so that helps.
Say that again, I'm sorry.
Sorry, my bad.
When it says you want to try another version.
Oh, yeah.
Then you try it and it's the same version.
Oh,
That
really?
helps.
Yeah.
So it gives you the answer.
All right.
Oh, yeah, I look at it.
Those are the ones I do first.
I'm happy of it. It's the same.
All right, there are your questions, what do you think, Melissa?
Sounds great.
Okay. Any other questions? Okay. Let's go on. Let's talk about limits to infinity. Now, if we take a look at this function, for example, and we take a look at the limit as x goes to infinity, let's look at this. Let's take this function right here, and let's take a look at the limit as x goes to infinity of this function 4x cubed minus 9x squared minus 15x plus 5. What would this limit be as x goes to infinity?
Approach that.
As x approaches infinity.
As x goes to infinity, as x increases without bound, what's going on with this function? What is this function doing as x Yes, it does. Very nice. It goes to infinity. Now, the answer does not exist. Where's Damien? I'm using his initials right now.
Getting.
Man, maybe he's just
Restroom.
a little bit shy and he
Yeah,
knew
he's
that
not-
was
he's not
coming
allowed to
up.
go to the bathroom? What?
Oh, man, he's not allowed when I'm going to use his initials, no.
You should have known.
Yeah, I know, geez. All right, that goes to positive infinity. If I were to ask you this on the test, okay?
Well, past 20 minutes. He said it was 20 minutes.
We're talking
Or
about, yeah.
resets.
It's probably 30 minutes.
Maybe
I
it's
guess
30.
it's 30 minutes.
Yeah, maybe it's 30. Anyhow, as x goes to infinity, this function increases without bound. There is no limit here, okay? It goes to positive infinity. And as x goes to negative infinity, what's the limit there? There is no limit. It's negative infinity. And if I were to ask you this in the test, which I won't, okay, the better answer would be the negative infinity answer, because that tells me what its behavior is. It's going to negative infinity. Go ahead.
Do you know that because it's a cubic function?
You know what? If it's any kind of polynomial, these limits to infinity will always be,
The same.
does not exist. Either go to positive infinity or negative infinity, depending on the signs of the function, okay? In other words, if I were to take this function and multiply it all by -1, the whole graph would be reversed. This would be going to negative infinity, that would go to positive. Polynomials never have limits as x goes to infinity or negative infinity. Never. They always either go to positive infinity or negative infinity. So those aren't very interesting. What are the interesting ones? Well, the interesting ones that are the ones that do have limits as x goes to infinity. And let's take a look.
4.5?
This is 4.5.
4. All right. When did we start 5?
What's that?
When did we start doing 4.5?
About 3 minutes ago.
As soon as you walked out of the room.
Yes. I said now's the time to do it.
And you use his initials.
All right, so here's where we are. Let's take a look at, and well, let's do this one here. Let's take a look at 1 over x. Go ahead.
Limits to infinity.
That's what we're doing?
Yes.
Okay. Thank you.
Let's take a look at this. We already know the graph. It's one of our basic 6. Let's take a look at the limit as x goes to infinity of this one. What's the limit as x goes to infinity here?
It's negative, right?
It's what?
Negative, right?
No? It's 0. As x increases without bound, the function's getting closer and closer to 0. How close to 0 does it get?
Really?
Really close. Really, really close. The word is arbitrarily close, okay? Does it get to within 1,000th of 0? Yes, it does. Just go out enough, it will get to within 1,000th. Well, does it get to within 1,000,000,000th of 0? Yeah, just keep on going. It will get to within 1,000,000,000th of 0. It will get to within any arbitrarily chosen small amount, okay?
Infinite.
Yeah, infiniteth. Yeah, that's a good.
Amount of-
Yeah, that's true. All right? This limit, because it is a limit, is a horizontal asymptote. When that limit exists, as x goes to infinity or negative infinity, okay, y equals that limit is a horizontal asymptote.
So wait, which zero is it approaching? The y one or
The x-axis. As x increases without bound, we're moving down the x-axis, the function, the y value, is getting closer and closer to 0, closer and closer to the x-axis, okay? That x-axis, y equals 0, is a horizontal asymptote. Y equals 0 is the equation of the x-axis. What's the limit here as x goes to negative infinity? Also 0. It's approaching 0 from underneath, but it's getting closer and closer to 0. That has the same horizontal asymptote as the x going to positive infinity. It has one horizontal asymptote, namely y equals 0. Okay? The functions that we do will have the same horizontal asymptote. That's not necessarily true for all functions. There are more complicated functions where the asymptotes are different. Okay? Yes?
Asymptotes are different when the denominator is like x plus 3, right?
Yeah, then you got vertical asymptotes as well.
Once the horizontal's up top then.
Here we go. This graph has a horizontal asymptote at y equals 0. But it also has a vertical asymptote. What's its vertical asymptote?
0?
Yes. It has a vertical asymptote, namely this line here, which is y equals 0. It occurs at x equals 0. Okay? That's its vertical asymptote. So you have two different things going on here. Vertical asymptotes. Graphs can never cross vertical asymptotes. Horizontal asymptotes. Those are the lines that the graph is approaching. Graphs may cross.
But they bounce back, right?
Yeah, well, what they may do sometimes they go like this. And then approach 0 this way. They may cross it over
They're
here.
gonna approach.
Yeah, they're still going to approach it as x increases or decreases, okay, without bound. All right, that's the simplest ones, okay? And let's get a little bit more complicated, okay?
How do you find the vertical? You do down the bottom one.
The denominator equal to 0, yes.
Yes. The horizontal you do both of them.
Well, you have to take the limit as x goes to infinity and see if the limit exists.
You can't take the top.
Well, it's a combination of the two, and that's what we're going to do now. We're going to take a look at some combinations that can occur. But first of all, you have to realize this. If the denominator has greater degree than the numerator, this has degree 1, this has degree 0, that limit as x goes to infinity will be positive or negative, would be 0, depending on whether it's positive or negative. It's 0, period. Okay? One's going to approach from above, one's from below, but we don't really care. So, it's a question of degree here. If we have this one, okay, let's take a look at this. We want to find the limit as x goes to infinity. What's that?
I don't know, wouldn't there be a bounce or something? Because it's two.
Not necessarily, no. But what we care about right now